attached to the wall physically.
Oh, you can?
So please.
Hi, everyone. Stergios is an assistant research professor at the University of Connecticut, affiliated with both Department of Civil and Environmental Engineering and Eversource Energy Center. He holds a 5-year diploma in civil engineering from University of Patras, a Master of Science in Hydraulic Engineering from Delft University of Technology, and a PhD in Civil and Environmental Engineering from University of Connecticut, where I have done my PhD as well, so we were colleagues back in 2019. He's a member of Technical Chamber of Greece, EGU, AGU, as well as American Society of Civil Engineers, and Associate Editor for Stochastic Environment Research and Risk Assessment, and a reviewer for numerous scientific journals. Stergios' expertise lies on the development and application of statistical and stochastic approaches toward the modeling of natural processes and engineering systems for risk assessment, design, and control. His current research focuses, but is not limited to, flood risk analysis and evaluation, probabilistic design of hydraulic structures, flood defenses, hydraulic variability, and climate change impact assessment, extreme rainfall analysis, as well as statistical downscaling. Thank you so much for coming, Stergios. It's really nice to have you here.
Thank you, Jagmur, and thank you for having me here. It's a great honor to be able to speak to you. And I'll go through the work we're doing at the center at UConn, and particularly I will focus on extreme rainfall and its relation to infrastructure and compound flooding in the context of climate change. So, as Jagmur said it all, basically, I'm Stergios Emmanouil. I'm a research assistant professor at the Civil and Environmental Engineering Department at the University of Connecticut, and my expertise lies in stochastic and statistical hydrology, with emphasis on whatever was described previously, emphasis particularly on risk assessment and extremes. To start with, in order to set the basis of what we will be discussing today, I would like to give the two definitions here of rainfall extremes and climate change. While climate change is mostly similar across fields, rainfall extremes, I find that in hydrology can be a matter of discussion. So for us, rainfall extreme refers to instances of unusually high intensity, which significantly deviate from average conditions that we have over a given area, and lie in the tail of the statistical distribution obtained from historical records, where we can apply extreme value theory. And the application of extreme value theory is basic here. And climate change refers to the long-term shifts and alterations in the atmospheric conditions of the Earth, which occur over decades or longer and can be driven by both natural processes and human activities. And mostly we're talking about human activities in the context of climate change and greenhouse gas concentration. So looking at these two, what we understand is that we have a problem that develops across different spatial and temporal scales, with different dependencies in time and space. There is non-stationarity, obviously, for the problem, and definitely we have also a problem of thresholds when we're talking about extreme value theory. So it's complex, and it's complex to link them together and actually get to robust conclusions out of any analysis. So, what is the relevance to infrastructure and public safety between extreme rainfall and how it develops due to climate change? It's a bit trivial, and based on the recent events that we saw through Spain, lately in Valencia, and also throughout the years in Germany and in the US, New England earlier this summer, natural weather systems evolve in such a manner that generally overwhelm more and more the current protection standards that we have. And for civil engineers and for us, this is a major problem, because current existing infrastructure, we expect it to last for a specific period of time, and right now we see these issues. So how should we quantify actually the vulnerability and risk that we have over the systems that we are working on, and ultimately organize adaptation strategies and protect this critical infrastructure that we have. So there are four main pillars that I'm going to go through in this presentation. The first one refers to the proper scales. As we said, it's a program of scales, and the proper tools to work with extremes. Then obviously we have the non-stationary nature of the processes we've been working on, and this has to be included into the equation. And then we have to somehow relate whatever we find from this non-stationary analysis to impacts and failures on the systems that we're working on, and ultimately look also in the interaction of rainfall as a variable with other variables that are drivers of hazards. So, starting with the proper scales, whoever has worked on hydroclimatic risk knows that we generally need multi-year precipitation data sets at adequately high spatial and temporal resolutions in order to work with identify risk basically and conduct hydrological modeling or any modeling. And lately, we've seen a series of generally atmospheric reanalysis products that offer quite robust global hourly estimates for extensive periods of time, which are, although rather coarse, to conduct general hydrological simulations and ultimately risk analysis. Then we have high resolution remote sensing-based rainfall estimates, and as for instance radar estimates that generally offer a pretty accurate depiction of the conditions over shorter scales, spatial scales primarily, and also they are pretty consistent in detail with the distribution, but the temporal coverage that they are offering is small, and this is a significant constraint for water resource application in general. So, while it really depends on the application, many applications require datasets that are shorter, and we can have analysis with shorter datasets. If we have this kind of problem, we can eventually find a way to merge the properties of different datasets through statistical correction and ultimately downscale certain datasets to obtain characteristics that we actually need in finer scales. So, such a framework we developed back in 2021 through an advanced QQ mapping scheme that was applied all over CONUS on a grid level of the stage 4 with a reference using basically the ERA5 dataset also as a reference. A statistical correction is generally a simple analysis, let's say, to think, but generally it has many little details that someone has to look at. As for instance, that the relationship that we have between the quantiles is considered time invariant, so we have a single relationship, and one has to account also for instances, especially for rainfall, like those when, for instance, the fraction of 0 between datasets is not matching. Then, because we're using a framework that actually uses a distribution mix, we're using, as you see, a log normal distribution for low and moderate rainfall quantiles, and a generalized Pareto distribution above a specific threshold in order to describe the tail adequately. Another question is, how do we define this optimal threshold? And we actually did that through a minimization of the Anderson-Darling statistic, and it worked pretty well across CONUS. So based on such a framework, we can actually get to a product that takes advantage of the advantages sort of both datasets that we're using, reference datasets, the era 5 and the stage 4. And here you see actually plots from a map basically of the errors we have over existing NORN gauges, which we used as a benchmark for the validation. And a period from 2002 to 2011 where the stage 4 data generally demonstrate that they have some inaccuracies, especially in the West. So, as you can see, the original stage 4 data set, there are certain inconsistencies which do not exist in the era 5 data set. And ultimately do not exist also in the downscale dataset, while the downscale dataset is also pretty accurate in the tails of distribution. It's pretty close to what the stage 4 described actually for the country. So ultimately this downscale dataset benefits from the strengths of era 5 and stage 4, and it offers an enhanced overall performance. Obviously, stage 4 is going to be really accurate over specific regions, but overall, the downscale data set is pretty consistent. This in terms of the data. Now, in terms of the tools, and I'm going to go through the tools that we use as civil engineers for infrastructure and are really relevant to our field. Especially for precipitation, how we design infrastructure. For many years, what we're using are the intensity duration frequency curves. And the intensity duration frequency curves are practically tools in which we can select a proper averaging duration based on the application. And based on a return period that is also defined from the application that we're working on, we can get into a design rainfall intensity. Now, as you very well know, there are some traditional approaches in order to derive IDF curves, and the most common out there are the peaks over threshold and the annual maxima approach, the annual block maxima. I'm not gonna go through them analytically, but one important thing is that they both assume stationarity, right? And something else important also is that generally we do not always have complete and extensive rainfall records to derive these intensity duration frequency curves with this approach. For instance, the annual maxima, they can be really limited when we don't have enough data. And also, when we apply those to longer series of data, we tend to conceal any climatic variations that we have. So the signal of climate change is lost. So what do we do? As I said, I'm not going to go through them. I'm going to go directly through the models that we use, and we use multifractal rainfall models. Now, for those that have never worked or have never heard about multifractals, temporal rainfall, we say that temporal rainfall is multifractal when its statistics remain generally unchanged when the observation axis, in this case the time, is contracted by a factor R, larger than 1, and then the rainfall intensity is multiplied by some random variable AR. And here you can see an illustration of the multiplicative cascades, which is generally depicts the reasoning behind it. And multifractal rainfall models have the advantages that use information from the full historical record. They provide a pretty robust parameter estimation even for really short records, and I'm going to show you in the results also a comparison between this and the other methods. And they provide the IDFs that are separable for D and T, which gives us greater flexibility in the way we describe the model and fit the model. One more advantage of the multifractal rainfall models is that we have an analytical solution. So while for the annual maximum, the peaks over threshold, we have to fit distributions and there is no analytical solution, here we have an analytical solution for the return period, and this can be actually turned into a relationship for the rainfall intensity. And four main parameters. Now these four main parameters, they are physically meaningful. You can see that they generally describe properties of the rainfall series, like the CPEP, which practically is the fraction of the interstorm dry periods. The log normal, which practically is the amplitude of the multiplicative fluctuations that you saw earlier in the cascades, and so on and so forth. D, the interarrival time of storms, and the mean rainfall intensity. So, going through a comparison of the two traditional approaches that we're using, the peaks over threshold and the annual maxima over a region in the northeast, and actually this is an analysis over 36 stations that had at least 60 years of data, full records. We see that generally for all studied averaging durations and return periods, the multifractal analytical approximation generally produces accurate and pretty robust IDF estimates, down to sample sizes of about 1 to 2 years, right? And you can see here the relative bias, the peaks over the annual maxima approach as we go to smaller, obviously, samples, the bias just explodes. And of course, in terms of the dimensionless RMSE, which encapsulates also the variability. So, sorry, I'm running ahead. So, now that we have established that we can work over the proper scales, right? And that we have the proper tools, and actually we have a tool that we can apply in a way that actually help us to define climate change, and I will show you why in a bit. Let's go to the effects of climate change generally on extreme rainfall, right? And over the last decades and even earlier, basically, we have seen that many researchers are trying to connect or link the changes that we have in precipitation extremes with simple thermodynamic relationships like the Clausius-Gladerian relationship, which essentially describes more intense and frequent extremes due to the rising temperatures induced by climate change, and seem to be generally valid at larger spatiotemporal resolutions. But if we go to the actual scales and resolutions that we're interested in for rainfall extremes and infrastructure resilience, their accuracy can actually be challenged due to the highly nonlinear dynamics that we have for rainfall systems, for instance, convective systems. Then we have climate model simulations that are multiplied over the years also. But these simulations do not explicitly account for small-scale convective processes. Of course, now we have also convection permitting models, which, however, are really computationally demanding, and it's difficult to set them up and run them consistently over large domains. And it's difficult to describe also the spatial distribution and evolution of regional extreme rainfall patterns, again, over areas of more complex terrain, or if we want to focus on a specific infrastructure. So, over the years, there have been many propositions in the literature of how parametric and non-parametric techniques can bypass these issues, and most of the approaches, as I said earlier, incorporate this assumption of stationarity. And this assumption of stationarity obviously introduces epistemic uncertainties into the final estimates. Some other approaches that propose how we could practically incorporate non-stationarity into traditional models. Normally, they incorporate distribution parameter estimates that vary with time. But as the parameters actually increase, we actually increase also the estimation variance. So they are equally inaccurate to the ones we see above. So what we proposed is an application of the multifractal approximation that we had earlier to really short segments of data, or adequately short segments of data, I would say, where conditions can be assumed stationary or reasonably stationary. So how do we do that? Obviously, we split the continuous hourly rainfall time series into sequential 10-year segments. For 10 years, I mean, we can assume, it's reasonable to assume stationarity. Then we fit the multifractal models to each one of these sequential decadal segments. And again, I'm reminding everyone that this is robust when applied to short rainfall records. And ultimately, we get something like that. We get a sample of rainfall intensity estimates for a specific return period and averaging duration that can range from 2 years to more than 100 years, actually up to 10,000 years or whatever we need. And based on this, we can practically find a trend. And this trend, of course, has to be checked whether it is statistically significant. In the paper that we had back in 2022, we're describing how we're doing this. We're practically creating a sample of, after mixing practically the segments, we're making different samples, and computation, we're looking whether the actual estimate falls outside of the distribution that we get for the mixed samples of 10-year segments. Okay, so this is what the shifted practically intensity, duration, frequency curves look for the same location that I was showing earlier. And as you can see, the red practically lines depict the intensity, duration, frequency curves that we had for a decadal segment in 1979 to 1988, in the 1980s. And this is what we get for the last decade, from 2010 to 2019. So you can see that generally IDF curves tend to move vertically, obviously, so we get higher rainfall intensities, but they also seem to rotate. So we have quite uneven changes across temporal scales, which is an interesting finding. That means that across temporal scales, the changes we have in the frequency differ. Now for the entire US, again, that was from the 2022 study, and here you see actually a probability density function of how the return periods from the 1980s, the 50-year actually return period from the 1980s, the 50-year rainfall intensity practically of the 1980s developed to the last decade from 2010 to 2019. And as you can see, across the US, the frequency of this same practically return level in the 1980s has decreased to more than half, regardless of averaging duration, which means practically that existing infrastructure that had been built for a reference return period of 50 years, and this is quite custom for stormwater drainage systems, for instance, will be overwhelmed much more frequently than before, actually twice as more frequently as before. And this is a major problem if we have two failures in a period of obviously. So the same logic can also be applied to climate model simulations, right? Here the scheme changes a little bit in the way we do it. Again, we have to downscale the climate model simulations, we have to bias correct them, and ultimately we have to use different models and apply the multifractal approximations and the schema I was describing earlier. But you can see again that regardless of the model and regardless of the period, actually, the 50-year rainfall intensity from the 1980s turns out to be halved in the different segments of time. Now, a really interesting finding that we had here, one is that you see that what we get from the era 5 downscaled, actually from the downscaled era 5 dataset that we have, is that the reduction is bigger. That means that climate models are likely to be underestimating what we will actually be getting into the future. And this is the RCP 8.5, by the way. This is the worst case scenario. And two is that if you look at the different periods for the models, and actually the ends of the different periods, right? You see 2010, 2019, 2041, 2015. The distributions tend to shift only a little bit. So one may be tempted to say easily that, okay, climate change tends to slow down, right? But this would be erroneous, because if you take as reference now the 50-year rainfall intensity that you had in the start of each of those periods, you see that the effect is the same practically. And here you see only one model, but the behavior is similar across models. So what we noticed is that climate change does not decelerate, obviously, but the effects of climate change are more distinct for lower exceedance probability levels. So for the tails, the effects are more distinct. And actually, lately that we were working with a completely different data set, this was basically on a data set produced by NCAR. We noticed that this same effect exists across the board for CMIP5 simulations, at least. That the effects tend to be more distinct in the tails of the distribution. Going to the relation that we may have with infrastructure, and we were lucky enough to have a big sample of about 300 locations where we had stormwater drainage systems, and actually we had culverts for transportation networks over the Housatonic River Basin. The Housatonic River Basin, for those that don't know it, it's a big river basin on the border of Connecticut, Massachusetts, and New York. And it spans the entire length of those borders and ends up in Connecticut, or in New York City, basically. Here we practically contrast the trends that we get for rainfall intensity over those locations historically. This is based on the historical records, and what we get in terms of failures for these culverts. And as you can see, the total failure rates generally follow the trends that we get for extreme rainfall excesses. And here we say rainfall excesses, not rainfall intensity, because in order to be able to compare the two, you have to somehow match the start. So practically we did some matching there of the rainfall excesses that would lead practically to this number of failures in the for the culverts. So across the basin, we see that the failure rates of water infrastructure tend to follow the trend that we see for 12-hour rainfall, which is pretty consistent with what we would expect for Connecticut and the types of storms that we have. We have more convective systems and less of larger storms that are characterized by averaging durations on the order of 24 hours or 48 hours. What we concluded is that essentially the water drainage systems that we have are totally unprepared to mitigate the impacts of heavy rainfall events, and this trend will continue to go up as we go forward. And this is a study that we will soon be submitting also for peer reviewing. Now, going to compound flooding, which tends to be a different kind of animal. Moving from univariate extremes to multivariate extremes it's a totally different approach that one has to follow, because what is an extreme in the univariate case differs with what is an extreme in the multivariate case. So in this case, we have to consider the inundation depth, since we're working with flooding, and consider it as a non-linear scalar function of a random vector of some selected predictors. In our case, for a coastal city like Boston, for instance, it would be SARS, rainfall, and streamflow, right? So, what we do is that we follow a two-step approach, a stepwise approach. So, we create an estimator for the inundation depth, and we can create also an estimator for the corresponding conditional frequencies. And that means that we can model linear and non-linear dependencies that we have for the conditional estimates and their associated probabilities in a separable setting. And again here, separability increases interpretability, increases flexibility, and allows us to work separately in the frequency domain and the time domain. So, for the time domain, right? And actually, for the time domain, we work in Gaussian space. So based on again the intensity, duration, frequency curves, and distributions, we pass everything to the frequency space, and there we fit a best linear unbiased estimator. Now, something that I consider important, it's the basics, is that generally the most robust way to approximate an unknown nonlinear function is to use a linear model. And that's why you use the blue model, which offers a covariance matrix that reflects the influence of the predictors over the domain, and also provides conditional estimates of the mean and the error variance. So we have also a sense of the variance of our error. And then for the frequency domain, and how the dependence of the frequencies, the nonlinear dependence of the frequencies can be described, we use trivariate copula models. And these models are between inundation, rainfall, and SARS, actually the non-exceedance probabilities of those three. We constrain ourselves to one parameter trivariate copula models because they are complex enough. I mean, going to more parameters or with trivariate copula models, it's really hard to estimate the parameters, especially from a constrained number of events. And ultimately, when we have a copula, we have an analytical form, and basically, through the analytical form, we can estimate conditional probability estimates based on certain combinations of rainfall and SARS. Now, two major assumptions here. The first one is that while the marginals may change, and sorry, it's low, maybe you cannot see it, but while the marginals may change, the dependent structure between the variables remains time invariant. That means that the relationship between the impact and the drivers remains invariant. And of course, the second one, the second assumption is directly linked to the first assumption. The dependent structure in the frequency domain has to be also time invariant. Otherwise, we would have estimates of, we will have two exceedance probabilities for one single inundation level, and that's impossible. So, about the experiment, here we're working with hydrologic and hydraulic simulations of historical storms that actually occurred over Boston from 2000 to 2019, and over a very, very fine grid that covers the entire greater Boston area. We're using an annual maximum approach in order to describe the extreme SARS levels, or the SARS levels at Boston Harbor. And the initial values also of event discharges at 5 gauges offered by USGS in order to somehow depict the conditions that we have, the initial conditions that we have over the domain prior to the storms. And we're doing an experiment here. Again, we're using the parametric multifractal framework for rainfall, but we're doing it as follows. For the first case, we're fitting the IDF curves to the entire sample of data that we have, right? So for the 20 years that we had, we're fitting one single IDF, we are producing one single version of the IDF curves. Again, remember that the multifractal model still assumes stationarity, but it's just robust into smaller segments of data. And for the second experiment, we are practically fitting the parametric multifractal framework in separate sequential segments as we did before. And this involves sort of a remapping generally of the quantile estimates and the associated exceedance frequencies in order to actually derive actual relations of how things are changing, but yeah, it can be done. And we contrast these two approaches for the 84 total storms that we have over the domain. And we will go through the results after I speak a little bit about the rainfall trends over the study domain, because I find this interesting. When we speak about rainfall, it's different to speak about the entire continuous records, and it's different to speak about events. For instance, if we look at the change of the 100-year rainfall intensities from 1979 to 2019 over Boston, you see a very clear upward trend, right? Where the 100-year rainfall intensities have a frequency of even 60, 65 years. But here, generally, we have fluctuations from segment to segment, right? And actually, if we go to the events that we have now from 2000 to 2019, you will see that the average shows a de-intensification over the domain, because just a section of the domain de-intensifies over the period 2010 to 2019, 2020 to 2019. But we also have significant intensification over extended areas, and look at the differences between the the approach that assumes stationarity through the entire record, and the one that's fitted to the segments. We have reduced variability, and the tail of intensification is much longer, while the areas of de-intensification reduce significantly. And what's important is that this reduced variability is from the model essentially capturing these climatic variations that was described earlier. So, going to sort of a comparison over the entire domain, what you see here are actually maps of the exceedance probabilities for the segment-wise approach over the exceedance probabilities for the entire sample. The conditional exceedance probabilities, right? Inundation on the left, rainfall on the right. This is for the entire domain over the available events. And you can see that we actually have increased exceedance probabilities for areas of rainfall intensification over there, the yellow areas where this relationship is larger than 1. Actually the most pronounced effects, and this is quite interesting, is that we get it in the most upstream locations where rainfall tends to be the dominant mechanism. So this is an intuitive result also, as it shows that rainfall influences more the areas where it tends to be risk-wise the dominant mechanism. While as we go closer to the shore, obviously SARS becomes the dominant mechanism of compound flow. So, going also to the blue model and how the actual inundation levels behave, here we see changes in the 100-year inundation levels over the domain through this fitted blue model that I described earlier. And again here you can see that for areas where rainfall intensify, the depths tend to be increased generally consistently. And while for areas obviously that we have reduced exceedance probabilities for rainfall also, we can see reduced exceedance probabilities for some of the cases of inundation. So, reaching the end basically in a summary and some takeaway points. The first one is that before trying to expand to novel techniques, and this is quite custom in the literature, we should first do some research on existing methods and carefully review them and find out how can we actually apply these traditional techniques correctly in order to answer the research question that we really need. Secondly, data generally for studies that try to relate climate change and rainfall should be really carefully studied and used. Despite the availability that we have, and we have a large availability of data, we don't know what the truth is. So we have to carefully look at the data sources and find out the ones that actually serve the application. Of course, existing water infrastructure failure rates seem to be following intensification trends of rainfall extremes over the areas that we're applying them, but what is actually the vulnerability of other systems, right? What other compound hazards can we look into? Can we look at rainfall and wind, for instance, for other systems? Or how can we adapt? What can we change in order to adapt to these changes induced in these hazards? And ultimately, extreme rainfall intensification seems to increase compound flood risk in areas where multiple hazards coexist. Of course, up until now we have results for Boston, and it would be quite interesting to see whether this is a cones-wide observation, what's happening over other regions where generally rainfall climatology and storm types differ, and how can we actually assess future exposure. This would also be interesting, how we could incorporate these trends that we see in climate models into the estimates of compound risk and antiviral risk. And with some of the selected literature that I'm sure you cannot see, I would like to thank you, and I'll be happy to answer your questions.
All right, questions for Stergios? Thank you for the talk.
Yeah.
Appreciate it.
Thank you. Yeah.
Hi, Stergios. Thanks for your talk. I have two questions.
Yeah.
First one is that to address the issue of non-stationarity, you divided the whole series into different segments.
Mm-hmm.
So you can assume stationary for each segment. So my question is that, consider that this all based on the historical data, will the derived IDF curve can really consider what is the potential of future extreme rainfall? This is my first question, because we can also adapt the update the IDF curves using the simulation of GCM models.
Mm-hmm.
So that is the more direct way.
Yeah.
So that is my first question. And my second question is that for the compound flood risk issue, like you said, you have a strong assumption that the marginal distribution can change, but the dependency structure is invariant.
Mm-hmm.
So in some cases, I think maybe because of the human activities, some kind of things that even if the marginal distribution is invariant, the dependence, like the response of the flood to the rainfall input,
Mm-hmm.
can also change. So maybe I have read some paper that consider the change of the dependency.
Yeah.
So I want to see your response.
Sure. So let me first go through the first one.
Yeah.
Generally, the segments show the evolution over historical records.
Yeah.
Given that historical records are more robust, they have already happened. And what we were trying to do basically through historical records is showcase that the climate is already changing a lot, right? So the approach actually, as I said, has been applied also to future data. But it really depends on what the application is again, and how you would like to apply this change, right? For instance, for IDF curves in this specific framework, right, if you bias correct and you downscale and then you run the analysis with the data set, you still can get a signal, right? Because it acquires information from the entire series of data about intermittency, about the magnitude of storms and interstorm periods. But if you want to go to a pure research, let's say risk analysis, sorry, where you have the actual distributions, the marginals, then most probably you would have to go with some relative changes that you get from climate models instead of going directly to the models, right? And through these relative relationship, essentially adjust basically what you have in terms of marginals from the historical records. Now, for the compound flooding question, basically, just assuming that the dependent structure will be the same is just a robust assumption to make, because we don't know actually how the system will evolve in the future, one. And assuming that the system remains the same, right, the infrastructure remains the same, actually the influence of the driving mechanisms, in this case SARS and rainfall, would be the same. It's reasonable to assume that. Now, for changes in the dependence structure, there are two ways to do it. If you want to change your fragility model, right, this we can do with purely parametric approaches. You have to have a different approach. You have to either have a mechanistic fragility model where you can work on actually a specific infrastructure, but then you cannot have a mechanistic model over larger scale application. You have to go on specific elements. Or you could create, and it's pretty common now, everybody's creating a digital twin, as they say, either through machine learning or anything else. You could create a digital twin of the system and describe sort of the fragility or changes, again, relative changes to the fragility based on this system. But again, you have to be really careful. It has to be relative. You cannot go directly and assume numbers just because you plugged in a data simulation, right? Regarding the marginals, if you want to look into the dependence of the marginals, for instance, SARS and rainfall, you could apply a copula and again see the relative change in the copula, for instance, or the dependent structure in future times, right, through the future simulations, and actually create also uncertainty bounds because the simulations may differ. But again, that means again that you trust the dependent structure that you get from the climate model simulations. And this is a big if, right? Do you trust them? Because climate model simulations, where they are good at depicting trends, they are also really limited when depicting dynamics of a system and how it develops. So as we go forward, I believe things will be much better in terms of the dependence, as you said, and newer studies and newer models and new setups will be able to describe that maybe. But for now, we consider that the safest thing risk-wise was to assume that this relationship remains stationary.
Yeah, and I think maybe we can just check if the dependency changes based on the historical data. If it changes or if it doesn't change, or
Yeah.
if it changes.
That's actually a good point. Someone could look into historical data and historical storms and look whether the dependency between the variable changes.
Yeah.
Or directly look at the time series, right?
Yeah.
Surely you can do that. But if you go to storms and specific storm events, if you go to an event-by-event approach, you are then limited there by the number of storms you have. And in order to fit, for instance, a copula, you have a significant amount of data in order to be able to fit it and estimate the parameters. Otherwise, it's highly likely that you will fall again into the loop of extreme uncertainties and biases. All this stuff. Yeah.
Thank you.
Any questions? All right, I'm going to ask one question, and it's going to be very practical. Can you go back just to your summary slides?
Yeah.
It's not technical at all. So the first 2 points there are a little bit of like words of caution.
Yeah.
Right? It's fair to say. So when you're working with the Boston Stormwater Department, they probably have technically minded people, but a lot of different utilities don't.
Yeah.
And they're gonna say, what data source should I use, right? What model should I use?
Yeah.
What are you gonna tell them, right? So from a practitioner's perspective,
Yeah.
what should they do?
It's then it's on us, I guess.
It's what? It's what?
It's on
It's on
ourselves. Yeah, it's on us. I mean, when and it's pretty common. I mean, for instance, in a DOE funded project that we're working now, generally everybody needs technical assistance because they are getting funds, but they don't know what to do with it. They're like, okay, what we're doing now, right? So it's sort of the question falls on scientists and the people that actually work, the engineers that actually work on these applications to decide what is the right data to use or what is the right tool to use. Now, if we go to infrastructure, for instance, we need generally fine temporal scales, fine spatial scales, and we need tools that actually can work on with extremes, right? In order to be able to actually solve the problem that we have over specific infrastructure spots, right? Yeah, that's my 2 cents.
Yeah, okay.
One question based on this first question. Why you take a 10-year time segment to consider the non-stationary? So is that means you're based on the 10-year data to fit an asymptotic curve?
Yeah.
But it sounds like in 10 years observation, how much days real events compared to a full time scale like 100 years?
Yeah.
So how would that change affect the accuracy of IDF? Does that mean like if I take a 10-year segment together, how it will be similar to like a whole 100 year?
Yeah. So good question. Okay, the 2 traditional models that I described earlier, right? The peaks over threshold and much more the annual maxima, right? What you said is very relevant because the annual maxima, if you have 10 years of data, for instance, you have 10 points in order to fit practically distribution and then describe what were the conditions over 10 years and try to relate them essentially to other parts of other decades. The model, the multifractal model is a stochastic model, and it practically reproduces, right, characteristics of the rainfall series, right? So, as I said, it has this set of really physically meaningful parameters that actually relate to precipitation as a process. So it can be actually robust even if you use 1 year of data. Can reproduce extremes even if you use 1 year of data, right? It's not so much about how many historical big events are there. It's what's the actual process that generates them, right? Yeah.
Any other questions? Any questions on that? All right, let's thank Stergios one more time.